Mrs. Traver here. Today we're going to talk about systems of equations, the special cases. Let's first review the three different types of solving them. The first one we had learned about was graphing, which is best used when lines have fractional slopes. Here's an example of that where I've got a slope of -5/3 and 1/3. You can see how if I was given this system of equations and I was going to try to solve it with substitution or elimination, it would be kind of annoying because I'd have to deal with the fractions all the way through. However, fractions are good for graphing slopes, so if we did this, we'd be able to find the solution where they intersect at 3, -2. The next one we use is substitution. This is generally students' favorite. It's used best when both or one of the variables is isolated. So here's one where both of the variables are isolated. It's got y equals for each equation. And in this one, we could just set them equal to each other to solve for x. Here's one where one of the variables is isolated. In the second equation, it's y equals. I could then plug in the x minus 1 into the y spot here to solve for x. Our last one we learned about is elimination. This is best used first off when both equations are in standard form. If they're not, you have to move it around to get it to that first. Also, when the coefficients of a set of variables can be eliminated with adding or subtracting. So in this situation, I notice they're all lined up, and I've got 4x minus 4x. If I add, those will cancel out. Another situation is one like this, where everything's lined up, and I've got 2y over 2y, which would end out just canceling if I subtracted. So these are the three that we've talked about so far, but what we've avoided so far is talking about two special types of solutions. So let's look at it now. One of them is when there's no solution, so there's no intersection of these lines. Take a minute and think about what the graph of this would look like when two lines are graphed and they don't cross. If you said parallel lines, you're on the right track because that's exactly what's going to happen here. So if I was going to graph these lines, I'll do the first one with an intercept at 2. And the slope is -3. So I'm going to go down 3, right 1, down 3, right 1, down 3, right 1. There we go. Or I could go up 3, left 1, up 3, left 1. So here's my first line. I'll do my best to connect the dots. There we go. My second one has an intercept at -5. And another slope of down 3, left 1. Down 3, up 1, or up 3, left 1. So as you can tell, these lines, if I could draw them straight, it would make it even better, but I'm doing the best I can. These two lines are parallel, so the graph looks like parallel set of lines, and that's what it would look like if we graphed it. Let's see what would happen if we solved it with substitution or elimination instead. So if I was going to solve this, I would use substitution since they're both set equal to y. I could plug this into here, so I'd have -3x plus 2 equals -3x minus 5. I then generally would try to get all the variables to the same side, so I would add 3x to both sides, and they'd actually both cancel. So I'd be left with something that looks like this, 2 equals -5, which is not true, like it's false. I have to put a not equal sign. So if we get something that is a false statement, we know that there's no solution because this could never happen. So therefore, they can never cross. Let's do one more of these. This one is y equals 4x minus 6. So let's graph it here. 1, 2, 3, 4, 5, 6. And my slope is 4x. So up 4 over 1. Up 4 over 1. Up 4 over 1. And I'm going to do my best again to connect these lines. There we go. My second one is not in slope-intercept form yet. I'm going to move some things around to make that be the case. I'm going to move the x's over. And then I'm going to divide everything by -3. So I've got y equals 4x minus 6. Notice these are literally the same line. So if I was going to graph this, I would just end up graphing it like on top of this one. So if our situation is looking at where they cross, these cross everywhere. They cross here and here and here and here and here. They literally cross in so many places. It's infinitely many solutions. So if I was going to try to solve this some other way, for example, say I was going to solve this with substitution. Let me go backwards to do that. If I was going to solve this with substitution, what I would have done is taken this version of y and put it in here. Let's see what happens when this plays out, because we know if we get something that's not true, like 2 equals -5, it's no solution. Let's see what happens if there's infinitely many solutions. So I'd have 12x minus 3 times the quantity 4x minus 6 equals 18. And then I would distribute this 3 in. So I'd have 12x minus 12x minus 6, plus, I made a mistake there, let me fix it. Okay, negative 3 times negative 6 is positive 18. 12x minus 12x, if I combine like terms, goes away. So I'm left with 18 equals 18, which is always true. So therefore, since something is always true, then there's always a solution, infinitely many solutions. Compared to the last one, if there's something that is false, then there's no solution. Here's another one. I'd like you to try this one out. I'm graphing it as well as using substitution. Take a minute and try that on your own now. All right, I hope you gave it a shot. Here's what I've got for mine. I've got my y-intercept at -4, and then I've rise 2, run 1, rise 2, run 1, and so on. So here's my line as best I can make it. Okay, that's what I've got. The other guy, let's see, if I was going to move some stuff around, I'm going to move over the 6x. And then divide everything by -3. So I've got y equals 2x minus 4, which is the same equation again. So in this case, it should be, I think that slide is wrong, infinitely many solutions. So that's what we've got for this one. The last one I've got here is I just want to kind of show us what this looks like in general. So with systems of equations, there's 3 types of ways this could play out. Either there is one solution, which is what we've spent most of our time on, where it crosses in one spot. There could also be no solution, where it crosses in no spots. And lastly, there could be infinitely many solutions, where it crosses everywhere. A way to look out for these 2 special cases, so these are the special ones. No solution is when the slopes are the same. So if you notice that, then you know it's going to be no solution because you know they're going to be parallel. Infinitely many solutions is a situation where they're literally the same line. So if you put them both in the same format, like both in slope-intercept or both in standard form, and they're the same, then it's going to be infinitely many solutions because it's essentially graphing a line on top of itself. That's all I've got for today. This wraps up everything we've got to do with systems of equations. If you have any questions, please feel free to ask in the comments, and I'll get to you there. Thanks, guys.